So this is the first video in a series of videos to look at rates of reaction or kinetics in the A2 CCEA chemistry specification. So we're going to start off pretty simple here. We're just going to look at how do we actually measure the rate of reaction and the practical techniques involved in that. And we're going to, through the series of videos, we'll develop the intensity up to proper genuine past paper questions and some of the most tricky past paper questions that have been set in the past. It would be really difficult unless you have studied these videos in class before to jump from the first video to the third video or the fourth video. So my suggestion would be that you start at the start and you work your way through them at your own pace. Okay, some of these videos will be relatively long, so I would also suggest setting 15 minutes aside and having a look at them then, rather than try to look at the entire video in one section. All right, so let's get started. So let's look at, first of all, what actually is the rate of reaction. What do you need to know it as? So it is essentially the rate at which the concentration of a named reactant or product changes, and that is with respect to time, of course. So we're going to measure rates of reaction in a change in concentration, which is moles per decimeter cubed, and we're going to look at that per second normally. So if we look at this, this is perhaps the graph that we might plot from some results that we get from a experiment, a rates experiment or kinetics experiment. Now, just very quickly, just to check that you're on the ball, could you tell me if that is a change in concentration versus time for a named reactant, or is this one that we have on the board here for a named product? Okay, so just pause the video and have a think about that very quickly. Okay, so this is of course for a named reactant, because you can see fairly clearly the concentration starts high and the concentration ends low. So obviously the concentration of whatever it is being measured is changing over time and it's decreasing over time. So therefore it is of course a reactant. And what you can see here hopefully is we have a really steep section. We have a sort of shallowing out section, and then we have an almost at the end here a section where it's almost plateaued, and this is representing the rate of reaction at the start when the concentration is high, rate of reaction is high. In the middle we can see it's slowing, and at the end hopefully we can see that the rate of the reaction is almost constant. In other words, the reaction has finished. And we can work out the rate of reaction by using this graph, which we get from our practical. And what we can do, if we wanted to get the rate of reaction at that point in the blue, is we take the gradient at the tangent. So you hopefully all know how to plot gradients. You learned that at GCSE Maths. If you haven't learned, if you don't remember that, go on to YouTube. Type in how to plot gradients to a curve. Okay, very simple. Okay, and remember, we're not doing maths here, we're doing chemistry, so it has to be a reasonably accurate tangent. Okay, so and when we do that, you can see that we can now get for this particular part of the curve a gradient which represents the change in the y, which is the change in the concentration, and if we look, that correlates to what rate of reaction is over here, and then we have change in x, which correlates to the change in time, and again that correlates to what rate of reaction is. And that means if we take these tangents, as we have just done, we can therefore work out the rate of reaction at this particular point. And if we did it here, and we did it here, and we did it here, we would find three different values for the rate of reaction. We would find at the start it is of course going to be the highest rate of reaction, middle it will decrease, and towards the end that will be the lowest rate of reaction. So you hopefully all remember from GCSE how to do that. Okay, and then you will of course have to work out your units. In this particular instance we have moles per decimeter cubed for our units of concentration, and on the x-axis we have time in seconds. So our rate for this particular measured reaction is moles per decimeter cubed per 1 second. Okay, and you can see of course that it decreases over time. Now we have a couple of different ways that we might measure the rate of reaction. We have initial rate of reaction, and that is right at the start of the reaction. Okay, so if we look at the graph here, we can see that the gradient is plotted at time equals 0, and that is a really good way to get the rate of a reaction, because we know what the variables are, we know what the temperature is, we know what the pressure is, we know what the concentration of our particular reactant that we're studying is at that point. Okay, so we prefer these, all right? And as I said, we know what all the variables are, the concentration. We're very confident of what the concentration is at this point because we've made it up, and we should know exactly what it is to a very accurate figure. We know what the temperature is. Now, some of you might go, well, the temperature wouldn't change during the reaction. But remember, reactions are exo or endothermic very often. So sometimes the temperature can go up during the reaction. Sometimes the temperature can go down. So not only would you be changing the concentration to work out the rate of the reaction in this particular one, the temperature might also be having an impact on the rate of the reaction. Okay? And you've been taught since you were probably 12, 13 years old that you always try to get a fair test where you change one variable and one variable only. And if you're changing concentration and temperature is unbeknownst to you also changing, that's not ideal. Okay, and we also know if there are any catalysts in the reaction or not at the start of the reaction. And some of you, again, I suspect, hopefully, are going, well, who on earth would put a catalyst into a reaction after it has started? Why would a catalyst change the rate of the reaction during a reaction? Well, you don't know about a thing called autocatalysis, right? And autocatalysis is very simple. Some products that you make during a reaction, I'm not going to go into too much detail, but some products that you make during the reaction actually act as catalysts. So as the reaction goes on, okay, you are making products. Okay, and some of those may actually act as catalysts. So at the start, they don't exist. So you know at the start that the only thing that's affecting the rate of the reaction is the concentration of the reactant that you are actually analysing. So hope that makes sense. Right, very quick, a few questions here, dead easy. Okay, so if you just pause the video, have a go at them, okay, and then I'll go through them very quickly. But they are very simple. So fastest rate of reaction, well, I think there's undoubtedly A, the concentration is dropping by far the fastest out of all three of the lines on the board. For which reactions A and B does the rate vary with time? Okay, so if we look at it, obviously at the start for A and B, they are very steep gradients to begin with, so the rate of reaction is high. They are moderate gradients in the middle, reaction is slowing, and then at the end, the gradients are pretty much plateaued. So therefore, the rate of the reaction for A and B over time will of course decrease. For C, how does the rate of reaction vary with time? Well, if you look at C, we said the rate of reaction was the gradient of the line. This is a straight line, so for those of you who are mathematical, okay, although you don't need to be that mathematical to work that out, the straight line has the same gradient no matter what part of that line you go from, so therefore the rate of reaction when I change the concentration of C is constant. Now that is completely new to you for A level. You would have always been taught that as you change the concentration of something, the rate of the reaction will change, and common sense almost tells you that, but we look at the reasons behind that as we go along. What is the initial rate for A? Well, hopefully what you did there was change in concentration. So if we look, let me just clear this off a bit. We start off at 0. So if we take our tangent, which has been plotted at time equals 0 here, we can see that the change, so we'll just go delta y. Delta y is 0.1 over delta x. Delta x, that's about 8, I'm thinking there, yeah. So it is 0.1 over 8 gives me, so it's 1/80th, okay. So in other words, 0.0125. Okay? Hopefully that all makes sense. If it doesn't make sense, take a little minute to have a look through it, guys, because the fundamentals that we're looking at there will be required for what we do later. So how do we get these concentration time graphs? This is our first step whenever we're doing these in class, is to carry out an experiment and to get a concentration time graph that we have on the board now. Okay, well, what you'll have to do is you'll have to follow, as I said, an experiment, and you will have to be able to suggest appropriate methods of experimentation to collect appropriate data to get your concentration versus time graph. So this is what this particular slide is here. You have sort of 4 ways in which you will be expected to look at an experiment that is described in an exam question, or even just in a balanced symbol equation, and you'll have to look at that information and you will have to come up with a suitable method, okay, or appropriate method to follow the rate of that reaction. So I'm going to go through a few of them here fairly quickly. Okay, you will know most of them already. Okay, so if a gas has evolved, well, you could measure either the loss of mass using a balance. Okay, you did that at GCSE, or you could measure the volume of gas that's produced per second using a gas syringe. And remember, there's no mention of timings in this, but you will always be collecting your data over a set time, or over whatever time you decide to collect your data. But it's always got to be a collective variable, okay? So in this case, mass lost or volume gained, okay, against time. The second one then is you will measure the pH change using a pH meter. Now, this is whenever, if you look at B is we are either making or using up acid, or making or using up alkali. And we can measure the pH of that with a pH meter, and that can tell us how much acid has been used up or made, how much alkali has been used up or made. Now, here's the thing. You haven't studied acid-base equilibrium yet, so you don't know how to convert pH into concentration of acid or concentration of alkali. But you'll just have to bear with us. Over the next few months, you'll study your acid-base equilibrium, okay, and you will be able to take your reading from your pH meter and convert it into concentration of acid or alkali. And provided you know the initial acid or alkali concentration, which you should know, then you can work out the change in concentration of acid or alkali per second. The other way to do it is quench the reaction. You'll see I've said quench the reaction here, which is new terminology to you, I would suspect. That just means stop the reaction. You do that a couple of ways. You either plunge it into a very cold ice bath, or you just throw a whole load of iced water into it. That does two things. The cold reduces the energy and stops successful collisions. The water reduces the concentration and dilutes it to such an extent that the reaction stops. Okay? And when you've done that, what you then do is you take an aliquot out of that quenched reaction mixture. Now, an aliquot is just a fixed volume. Usually, we would take 25 cubic centimetres, and you would titrate that against a standard solution of sodium hydroxide or maybe hydrochloric acid. And that will allow you to carry out a titration to work out the new concentration of acid or alkali in your flask. That, I believe, is one of your CCEA assessed or prescribed practicals, so please make sure and learn it. The next one is definitely an assessed practical, and it's one that's learned very badly. Please learn this one, and I'm not going to go into it in too much detail here, okay, but it is an important one, and it's worth a lot of marks if it comes up in a summer exam. So this one, you have a coloured reagent that's either being used up or it's being produced from a colourless solution. Now, the ones the examiners like here are bromine or iodine. Both of those are coloured, okay. Iodine is sort of a dark brown, and bromine kind of an orangey brown. Don't confuse these, please, with bromide ions and iodide ions, both of which are colourless in solution. All right, so please be careful. The halogens coloured, the halide ions not coloured. And if we're looking to measure the intensity of colour, what we use is a thing called a calorimeter, and we use a calibration curve. And a calibration curve basically means we read off the calorimeter the intensity of light that is being produced or that is being allowed to pass through the reaction mixture. Okay, so in other words, we can work out how much light is being absorbed by the reaction mixture. And as you can hopefully imagine, the darker the reaction mixture, the less light is passed through it, or the more light is absorbed. And also, therefore, the darker the reaction mixture, the more bromine or iodine happen to be in there. So we can make a correlation between the light absorbed and the concentration of iodine and bromine. And when we get that value, we then read off a calibration curve from the calorimeter that we have made ourselves, okay, in preparation for the experiment. And then you can say what the concentration of iodine or bromine is at a particular time. Okay, I'm not going to read up on calibration curves. Okay, it's too lengthy for me to start getting into the detail of that here and now. If we have an overall change in the number of ions, okay, well, we can measure that by a change in conductivity using a conductivity meter. That's not really on the CS spec, but I put it in here anyway. Okay, just in case it might pop up for some reason, they could still give it to you and give you some information about it. Right. So you want to pause the video here. You have got 4 experiments above, okay, and you have to work out which of those methods are suitable in order to follow the rate of the reaction. Some of them have a couple of suitable methods. Okay, so pause the video now, and then I will go through them. So the first one, hopefully you picked up on the fact that we have ethanoic acid here. So therefore we can use change in pH. There's no other one in there. There's no gases being made. There's no change in ions. Nothing in there is coloured. So we can't use any of those other ones. So you can use a pH meter. You could have said titration, quench, and then carry out a titration. That would be fine. It's not an option there, but you could do that. Second one, You can use a gas syringe, I think. Hopefully most of you will pick up on that. Carbon dioxide is being made. There's no gases on the left, so you're making carbon dioxide. You could have used loss and mass. In fact, this is what you would have done at GCSE, where you did exactly that. You used loss and mass because the carbon dioxide will leave the reaction flask, and it's quite a heavy gas too, so you can easily measure the change in mass. The other thing you could have used here was a pH meter, because you can see hydrochloric acid is being used on the left-hand side, and nothing on the right-hand side is acidic or alkaline. So you could use pH meter or quench the reaction and titrate against standard sodium hydroxide. The next one is conductivity. Okay, on this left-hand side you have 2 ions, and on the right-hand side you have 3 ions. So you would change the number of ions, so you would change in conductivity. And the final one is one that you may well have done at GCSE, okay, where you have iodine being made. So you have a colourless solution on the left and you have a dark brown solution on the right. So you would have gone colorimeter in that one. Okay, you can also, if you wanted to use conductivity, you have 3 ions on the left and you have got 2 ions on the right, so conductivity would have been fine. Okay, don't think you can use any others in there for that. So hopefully you got those all right, and you can sort of pick out. And that's kind of how an exam question will come to you, either in words or with an equation like that, and you'll be asked to suggest an appropriate method. You'll may well be asked to describe how you use that appropriate method as well, by the way, but that is on the same prescribed practical, so make sure that you learn those. So now we're going to look at how we would actually monitor the rate of a reaction, and there are 2 methods that we have to be familiar with. Okay, there is one, first of all, which is the continuous method, and then we'll look at initial rate only methods. So these are pretty simple. You'll have done these probably in the past. You've certainly done continuous one in the past. Initial rate, perhaps not, although I suspect back at GCSE, when you did rates of reaction with temperature or concentration, you most likely have done this as well. We wouldn't have referred to it as initial rate or continuous monitoring back then. We would have just called them a rate of reaction experiment. So with a continuous one, which is the one you're most likely not to have done, you basically take a single reaction mixture, okay, and the concentration of whatever your chosen reactant or product is in that, okay, and we've sort of looked at the methods and the reasons why we might choose a particular reactant or product to measure on the last couple of slides. Okay, you will measure at regular intervals, okay, the change in the concentration of that particular reaction or reactant, or product throughout the experiment. So it's just basically one experiment, okay, and you let it run, and as it runs, you measure the change in concentration of reactant or product as that experiment happens. And we'll look at some example experimental data on the next slide over. Okay, and for that, the rate at time t is equal to the gradient of the concentration time graph. So you do your experiment, you plot your concentration of your reactant or product that you have chosen, okay, and you plot that against time, okay, and at the particular time, okay, that will give you the rate of a reaction, okay, and we'll have a look at the graph on the next slide over. Initial rate only, okay, is where you do several different experiments, several different reaction mixtures you will use. Okay, and each will have a different variable. Okay, so for example, you'll change the temperature, okay, from experiment 1 to experiment 2 to experiment 3, or you change the concentration, experiment 1 to 2 to 3, okay, of your chosen reactant. Okay, and you'll have done these before. You'll definitely have done these at GCSE. Okay, and for each, the time taken for a fixed change in concentration is measured. Okay, so you will measure how long it took, for example, to make 50 cubic centimeters of gas. You will take how long it took for a particular concentration of, let's say, sulfur to be made. Okay, and the initial rate, okay, which will be equal to the change in concentration over the time taken. Okay, and remember the change in concentration is constant. And okay, if that's what you've decided to measure, you're measuring the same change in concentration every single time. Therefore, we can say that the initial rate is equal to 1 over the time taken for that change in concentration to occur. Okay, So that is how you work out your initial rate. And you would have done lots at GCSE. You worked out the rate of reaction as 1 over time. And the reason why is because you were measuring the same volume or the same concentration change every single time. The thiosulfate hydrochloric acid experiment would be a prime example of that. So if we look at a continuous measuring or continuous monitoring experiment here between hydrochloric acid and magnesium, if we take fixed volume of 0.1 molar hydrochloric acid and we react it against a mixed mass or mixed amount, I should probably say, of magnesium, okay, at a fixed temperature, and we work out the volume of hydrogen that's collected every 5 seconds. So that is our continuous monitoring. Okay, and we get a graph like this. Now, if we remember back, we can then use this graph to work out the rate at particular times. Okay, and how do we do that? Well, very simply, we draw our tangents to the graphs at those particular times. Okay, so the volume of hydrogen formed at 5, 10, 15 and 20 cubic centimetres. How long did it take for those volumes to form? Okay, and we can see that we're looking at our tangents on the right hand side. Okay, so we have change in y. For the first one is 4 over 5, second one 3 over 5, third one 2.5 over 5, okay, and the final one 1.5 over 5. So we are measuring change in volume against time. Okay, and therefore you can see quite clearly from the graph, but now we have it quantified, that the rate of the hydrogen formation at the start is very high, 0.8 cubic centimetres per second, okay, and the rate slows down as we go through the experiment. So we're cubic centimetres per second. Okay, here we are 4 over 5, which is our 0.8, and then we get right down to the end where we're still using a 5-second interval, but our amount of gas that's made in that time this time is only 1.5, and therefore the rate, okay, which is the gradient at that particular point, has changed. It's now 0.3. So that's what continuous monitoring looks like. Initial monitoring then would be where perhaps we take, in this instance, the same amount of magnesium with a same volume of known hydrochloric acid, known concentrations of hydrochloric acid, and same temperature. Okay, and at this time you can see, if we have had different times taken. Okay, so at the low concentration, okay, it was 27.8. At the high concentration, it was 5.6 seconds in order to make our fixed volume of hydrogen. Okay, so from there on in, because we are making the same fixed volume of hydrogen every single time, we can treat our rate as 1 over time, because our change that we are measuring is the same every single time. And if we do that, we'll see that the rate is very low at the low concentration, and it is much, much higher at the high concentration, which is kind of what we would expect. Okay, so we have run, in this instance, 5 different experiments, okay, with 5 different concentrations of hydrochloric acid. It has taken us 5 different time intervals to collect, in this case, 10 cubic centimetres of hydrogen gas. That is what we're measuring, and that is constant. Therefore, we can treat that as 1 over time. And our units this time are just per second. Now, kind of leading into why that last couple of slides are important, you need to know about continuous, you need to know about initial rate monitoring, but also, okay, we're going to look at how can the rate measured in terms of one reactant or product be converted to the rate with respect to another one, okay? So for example, in this particular equation, if we look at it, we have worked out that the rate with respect to iodine, okay, is 0.0025 moles per decimeter cubed per second. So we've carried out our experiments, okay, change in concentration over time, okay, and we have worked out that the rate at which iodine is being made in that experiment is 0.0025 moles per decimeter cubed per second. Now, how do I use that then to work out the rate at which sulfate ions are being made or iodide ions are being used up, okay? Right, this is very easy, but it's very useful because you will need it in some questions. It is to do very simply with the ratio in the equation. So for example, if we look at iodine, okay, to S2O8, two negative ions, okay, they are in a 1-to-1 ratio. So the rate at which iodine is being formed is equal to the rate at which the S2O8 two minus ions are being used up. Therefore, hopefully you're starting to see that therefore the rate at which the iodide ions are being used up is that multiplied by 2, because it's a 2-to-1 ratio, iodide to iodine. And then finally, if we work out the rate at which the sulfate ions are being made, they are exactly the same at the rate of the loss of iodide ions, okay, because they are in the same ratio. Okay, and that does confuse people a little bit in questions. It's a very simple principle behind it, so hopefully that helps you there. Okay? Now that's as far as video 1 goes, guys. Hopefully that's a lot of those things are just the principles which you will have to apply as we go deeper into this topic. Okay, so please make sure that you have a good idea of what I've spoken about there. Okay, and then we'll have a look at video 2.